dr. Ahmath. Welcome to the course of multivariable calculus. In this lecture, we're going to continue our discussions about the infinite series, and we're going to talk about one of the most important, interesting, and fascinating types of the series, which are called the geometric series. So we've seen the geometric series before at school as well. And in general, we can write down the geometric series in this form, where the first term, a, so a is going to be the first term, and the second term is going to be obtained by just multiplying the first term to some r, to some common factor r. So you can see here that the second term is obtained by just multiplying the first term to r. And we are going to obtain the third term here by just multiplying the second to the r again, right? So we are always going to obtain the next term by just multiplying the previous one to some number r, and we are going to call this number r as the common factor. So in a compact form, using the sigma notation, we can write down the geometric series in this form. So it's going to be a, which is the first term, times r, which is the common factor, in the power of n minus 1, when n is going to start from 1 and goes until infinity. So where a is not equal to the 0. So let me give you a small example, then we're going to continue about estimating the sum of the geometric series. So for example, you might have a geometric series which is going to start from 1, and we're going to always obtain the next terms by just multiplying the previous ones to the 1 over 2. So in this case, the common factor is going to be equal to 1 over 2. So the next term is going to be 1 over 2 plus then 1 over 4 plus 1 over 8 plus 1 over 16 plus and so on. So this is an example of a geometric series. So another example might be when we have the when we are going to start the series, for example, from 5, and the common factor is going to be equal to the 2. So in this case, we're going to obtain the next one by just multiplying the previous one to the 2. So it's going to be 10 plus 20 plus 40 plus 80 plus and so on. So in this case, the first term is going to be equal to the 5, and a common factor is equal to the 2. So now the question is that is it possible to estimate the sum of this infinite series? So is it possible to know whether this sum, the infinite sum, is going to converge or diverge? So when we say the converge, it's going to be, so the sum is going to be a finite number, and diverge means like either it is undefined, either it's going to be plus minus infinity. So in order to do this, we are going to derive the formula of estimating the sum of a geometric series. So we are going to introduce the partial sum, which is going to be the sum of the first in terms of a geometric series. So the first term is a, so let me guess what is going to be the next term. The next term is going to be a times r. So the next term is going to be a times r in the square, plus and so on, and the nth term is going to be a times r in the power of n minus 1. So if I just multiply Sn to the r, it's going to be r times Sn, right? So let's assume that I know what is the sum here, right? So what I'm going to do is I'm just going to multiply both of the parts of this equation to the r. So the left hand side is going to be simply r times Sn, and the right hand side part is going to be a times r plus this term is multiplied to the r, it's going to be a times r in the square. So this term multiplied to the r, it's going to be a times r cubed plus and so on, plus a times r in the power of n. So what I'm going to do now is I'm going to subtract these two rows in equations. So on the left hand side, I'm going to obtain Sn minus r Sn, right? And on the left hand side, I'm going to just subtract all of these terms from this one, right? So if you do this, you can see that some of the terms are equal, right? For example, this term and this term are equal, and if you subtract them, they're going to be just cancel each other. And this term and this term are equal, this term and the next term here are equal, and so on. And the only two terms which are going to left is the first one from here, which is the a, and the last one from here, which is going to be a times r in the power of n, if we subtract the equations into two rows. So what I'm going to do is our ultimate goal to find the Sn, right? The partial sum. So this is going to be equal to, so 1 minus r if you take out the Sn from the brackets, and here if I take a from the bracket, it's going to be 1 minus r in the power of n. So Sn, the partial sum, is going to be equal to the a times 1 minus r in the power of n divided to the 1 minus r. And in general, so this is the partial sum. So if you write down the geometric series in this form, a times r in the power of n minus 1, when n goes from 1 to the infinity, right? So its partial sum is going to be equal to the a times 1 minus rn divided to the 1 minus r. But this is just the sum of the first n terms, while here on the left hand side we have the sum of all the infinitely many terms, right? So that is why we have to find its limit when n goes to the infinity, right? So it appears here, this is the formula of estimating the sum of the geometric series. So now what we need to do is we need to try to figure out when the sum is finite, actually. So the Sn is equal to this formula. So let me write down the formula for the Sn one more time. It's going to be a times 1 minus r in the power of n divided to the 1 minus r. For which value, actually, of the r, the sum is going to be finite, and for which value of the r, the sum is going to be infinite. So it appears when r is in between minus 1 and 1. So let me give you an example. For example, r is equal to the 1 over 2 or 0.6 or whatever. So the r in the power of n and its limit when n goes to infinity is going to be equal to 0 if the r is between minus 1 and 1. So if r is out of this region, basically is bigger than 1, and at the same time r is smaller, or r is smaller than minus 1, then the limit of r in the power of n when n goes to the infinity goes either to the plus infinity, either goes to the minus infinity. So we've got the conditions that, hey, the geometric series is going to converge to some number if r, the common term, is between minus 1 and 1. And what is actually its limit? So let's assume that we've got a geometric series. We have the geometric series. So in this case, we are going to write down the geometric series as a plus a times r plus a times r squared plus and so on, plus a times r in the power of minus 1 plus and so on. So compact form, we can write down this a times r in the power of n minus 1, and goes from 1 to the infinity. So this is actually equal to the limit of a in the power of 1 minus, a times 1 minus r in the power of n divided to the 1 minus r when n goes to the infinity. So if r in the module is less than 1, which is equivalent to say that r is between minus 1 and 1, then this limit is going to be equal to, so then the limit of partial sum when n goes to the infinity is going to be equal to the limit of a 1 minus r in the power of n divided to the 1 minus r when n goes to the infinity is going to be equal simply to the a times 1 minus r, right? So since this term is going to be equal to the 0. So we've got the formula to find the sum of infinite geometric series. So the sum of r in the r in the power of n minus 1, n goes from 1 to the infinity, is going to be equal to a divided to the 1 minus r if r is between minus 1 and 1. Otherwise, it is going to be divergent. So otherwise, the geometric series is divergent. So let us do a couple of examples of estimating the sum of a geometric series. So let's start from the first example. So estimate the sum of the series 5 minus 10 over 3 plus 20 over 9 minus 40 over 27 plus and so on. So obviously the first term a is going to be equal to the 5, and in order to find a common quotient, for example, or a common term, common ratio, we can just divide the second term to the first one. For example, second one to the first one. It's going to be minus 10 over 3 divided to the 5. It's going to be minus 2 over 3. So this is the common ratio. So we can check that so whether this common ratio is correct or not by just multiplying the second term, which is minus 10 over 3, to the common ratio, which is minus 2 over 3. We are going to obtain 20 over 9, which is exactly equal to the third term. So we have calculated or figured out the important attributes of the geometric series, basically the first term and the common ratio. Now it is possible to find the sum of this geometric series, right? So since the module of the r, which is going to be 2 over 3, basically the absolute value of the r is 2 over 3, which is less than 1, then this geometric series is convergent, and the sum of this geometric series is going to be equal to the first term, 5, or let me write down the formula. The first term divided to the 1 minus r. So it's going to be 5 divided to the 1 minus 2 over 3, right? So it's going to be equal to 5 divided to the 5 over 3, which is going to be equal simply to the 3. So this sum of the series is going to be equal to the 3. So it is very easy to calculate the sum of the geometric series when we actually know the first term and the common ratio. So let's do a couple of more examples. Example 2. So in the second example, we need to estimate the sum of the series 2 in the power of 2n times 3 in the power of 1 minus n. N goes from 1 to the infinity. Actually, it is not so easy to see that this is a geometric series, since it is written in a very not in a standard form, right, without n. So we need to try to bring this series into the standard form, and I say I mean by the standard form this form. So a times r in the power of n minus 1. N goes from 1 to the infinity. So some term times another number in the power of n minus 1. So let me write this down. So it's going to be a sum of n goes from 1 to the infinity. So 2 in the power of 2n can be written as a 4 in the power of n, right? And at the same time, 3 in the power of 1 minus n can be written as 1 over 3 in the power of n minus 1. Right? So one more thing which I wanted to do is I would like to write down this as sorry, so I had a mistake here. No, not a mistake, but probably it's easier for me to write this as this 3 in the power of 1 divided to the 3 in the power of n, right? So I think this is better, because we know that for the exponentials, so this is going to be exactly the same as the 3 in the power of 1 minus n. So it's going to be the sum. So 4 divided to the 3 in the power of n times the 3, right? The thing is, we need to have the term in the form of n minus 1. So that is why I'm going to take out 1 times 4 over 3 out of the brackets. So basically I'm going to write this in this form. So 4 over 3 in the power of 1 times 4 over 3 in the power of n minus 1 times the 3, right? So now this is correct, because like if you just multiply this, you're going to get exactly 4 over 3 in the power of n. So it's going to be the summation of this 4 over 3 times 3 is going to be simply equal to the 4. It's going to be 4 times 4 over 3 in the power of n minus 1. So we brought the series into this form, which is like the standard form, and it's easier for us to extract the important features of the geometric series from here. So in this case, the first term is going to be equal to the 4, and the common ratio is going to be equal to the 4 over 3. So since the common ratio in the model is more than 1, then the series is divergent. So in our lectures, we're going to solve a couple of more problems on the geometric series. So far, this is the geometric series and how we need to work with the geometric series and estimated sum.